Yeah, so the R Java is only for running Maxent in R. For the GIS analysis, spatial analysis, we don't need that. And I think we're going to get to the running Maxent in R maybe in the afternoon. So we still have our lunch break if you want to still fix the software issues. So generally speaking, the workflow of running Maxent in R is we're going to obtain our occurrence data. We clean our data, then we make it spatial, and then we can also do more filter after they're spatial, because we can do different things. We cannot do that before they become spatial. Also for the environmental data, where they download the data, load them into R, we manipulate the data into the desired resolution and extent, and then we define the study area. Then we not manually, but we have to define how we're going to select the background points. So if you use the Maxent Java interface, the background points are randomly selected. But here in R, I prefer to select it manually through a line of code, because you have a better control of what is being selected. So after we got the occurrence data, after we got the background points, we're going to extract the environmental conditions associated with those points. And then we format those environmental conditions into a correct format. We feed the data into Maxent. And then we can, after we obtain the model, we can evaluate our model. Then we can also do projections. I want to be clear about what is a model when we're talking about a model, because a model can have many different definitions. So we have our occurrence data, we have environmental data, we do the model training, and then we get a calibrated model. With this model, we can make prediction on our training data, make prediction on testing data, make predictions to another continent, to another time. So when I say model, this is the model. But if you use Maxent interface, maybe all of this happens at the same time. And I will say a prediction is not a model, but something in the middle. It's more about the parameters of that model. That is a model when I say model. And if you open the HTML file, that will give you an outline of the code. And I think even if you set up the package without me, you can successfully run through everything. But with me, I can probably better explain what we are doing here. So first of all, we load all the packages. And I have a bunch of comments for what is that package used for. So for raster data, we use the raster package. The decimal package is a collection of very basic tools or functions for niche modeling. And then we have our RGOS, RGDL, SP. Those are mainly for spatial analysis. And there's another package called ENMEVAL, which it also provides a few functions that help you build either simple or complex niche models. And then the utility is based for downloading data, and for zip and unzip files, and the JSON lit is for downloading data directly in R. After you successfully load all the packages, if you want to run Maxent in R, you have to put maxent.jar in a special folder. And this code will help you do that. It will first download the 3.3.k version of Maxent and place it here in a folder underneath where decimal package is installed. This would automatically copy and paste that maxent.jar file into that folder. And then we're going to go into the environmental data manipulations. So first of all, I created a bunch of folders that we're going to use to store the environmental data, store the temporal data input, and also the final output. And this part basically downloads the volt claim data from the volt claim server automatically, and also unzip it. If you notice, their server is UC Davis because the author Hyman is from UC Davis, so they have a server there. And then after we got these files unzipped, we want to load them into R. And this code is going to help you figure out what is the path of all the environmental layers. So have anyone tried to successfully run until here in their R? Okay. So the first parameter is the path of that folder. And the second parameter is a regular expression. I put .bil and the $sign. Basically the $sign means the end of the name, the end of the file name. And the BIL basically tells you find any file that ends with .bil. So basically I'm gonna find all the BIL files within this folder. And this would give you a list of the files. And if I run that in R, this would be the files that are kind of the path of all the files. And then we're going to use a function in raster, which is going to raster stack. Stack basically load a lot of raster layers at the same time. And there's another function called raster. Basically, that one can load one layer at one time, but the stack loads a lot of things at one time. However, the assumption is all those files have the same extent, same resolution. Otherwise, you cannot load them at the same time. So after we load this, we can actually, if you run this, the claim this variable is a list of raster layers. You can put 1 if you want to look at the first thing in that list. And if you tap it, it will give you the attributes of that layer. And so basically, it tells you this is the dimensions, how many rows, how many columns, the number of cells. This is the resolution. This is the extent in coordinates, and this is the coordinate system for this layer. And this is the name of the layer. This is the value of that layer. So it will give you a summary of this raster layer. And if we continue, yeah, obviously you can use the number of rows, number of columns, and extend to look at each attribute one by one. And here, this is the function for to make a new resolution of a layer, say resample. Here, this function is going to give you a layer that is 10 times coarser. So here what I did is I first defined a new raster, which has, and the number of rows and the number of columns are going to be 10 times smaller than the original layer that I just loaded, which is bil1. And then here I defined the extent of this new raster layer using the previous bil1 layer. And then this resample is going to give you a new raster layer that is at a coarser resolution. So the first parameter is the original input, say bil1. The second parameter is this new raster layer, and then you can select different methods. This is, you know that in ArcGIS there are different algorithms to do this interpolation, and you can also do that in R, but you have to specify that specifically here. And in R, you can easily plot this raster by using plot. And here's the map of that bil1 layer. And this is our new layer, so obviously it looks coarser. It's easy to see that. And also sometimes this function can be very common. Say we got our prediction of Maxent. We want to threshold the prediction. And here's what I commonly do. It's called reclassify. Before you do the reclassify, you have to define how you're going to classify it. So if you look at this, the structure or the values from here, so there are going to be, you have to put three parameters at one time. The first parameter is from to the new value. Say, for example, if the value is from ultimate small to 100, this algorithm is going to assign 1 as the new value. And for example, if we have a Maxent prediction, you want to use our threshold, say 0.1, and here maybe you're going to put from 0 to 0.1, then the new value is maybe 0, and then from 0.1 to maybe 1, you're going to assign that as 1. So here's how I usually thresholded my Maxent predictions. So make sure you have 3 parameters at one time. And then you can, this my method, load this into, give this classification method to reclassify function. And then if you look at this map again, it has only 2 values. So it is a thresholded map. And the other good part of R is you can easily manipulate your raster layers, say the calculations. So first of all, we can stack the 2 layers. They're arranged, as I mentioned earlier, you can load 1 raster layer at one time using raster function. And you can stack them together into 1 raster stack. And you can plot this stack at one time. So far so good. Okay. And here, basically, I plotted the 2 layers at the same time. So to do calculations, you can easily do some simple math in R. Here, what I did is I have 2 layers, wet and dry. I just use wet minus dry. I get the difference. And this difference is a new raster layer. And you can achieve the same results by doing this. You put them together as a raster stack, and you provide a function to here. So it's CALC, basically do some calculations for raster. Here the function, you can provide more complex functions that you can define it. And here mean it itself is a function in R. You can see that in R if you tap mean. It will tell you this is a function. So the second parameter is a function. And similarly, you can also do the mean of the 2 layers, wet plus dry divided by 2. And there's also an easy way to show you the values. You can use hist, basically the histogram of the values in that raster. We know that it's available in ArcGIS, but it's also even easier in R. And then there's the histogram of the values in this layer. Commonly, we do the correlation analysis of your layers. Say you want to look at the congruality among 90 bioclimatic variables. You can use this pairs. The function can directly compare the correlation between the layers. It will give you a matrix of figures. That's the histogram and also the correlation coefficient. I think that's some basic steps for spatial data manipulation that are necessary for this Maxent modeling in R. And then I'm going to go to occurrence data. So any question for the raster part? You're curious or you want to know? Okay. Okay, so occurrence data, we know that there are a lot of databases, they have APIs. Anyone don't know what is API? Or anyone know what is API? Okay, so API is basically how programs talk to the database. If you tell the database, give me the armadillo data, they will not give you any answer. But you have to formulate a bunch of formulas, put that into a script code, throw it to the database, it would give you the data. So that script of code is called API. And obviously in R, we can easily code it and directly submit request to say gbif, and then the gbif will return data to R directly. And there's a function called gbif. There are the two important parameters. The first parameter is the genus name. Second parameter, the later half of the species name. If you run this, Maxent would, no, not Maxent, but R will directly download data for you. But you have to be online. You have to have internet connection. Yes.
That package, the required JSON liker, I don't know how you say it. So is that specifically just for gbif, or are there other packages? Do you have to download separate packages essentially to connect to different databases?
Yes. That's a good question. So this function, gbif, this is not the official API developed by gbif. I think gbif has another API called rgbif, but it's only available recently. And this gbif function is available a long time ago. It is written by Hyman, who is also the author of Word Claim Dataset, who is awesome. So this JSON-lit package, it is basically to help you to formulate the request that is used to send to the gbif server. So this package may be necessary for other tasks if you want to download something else. And also, so another question that you mentioned, I think there are going to be different packages for different databases. I know that for IUCN, for example, those range maps, you can also, there are packages you can use to directly download range map in R. But they may request a special key you have to apply.
Will that information be made available to us somehow? For like the big databases or something, like the key packages, if you have that on hand?
You mean IUCN?
Yeah, like if there's multiple, if there's only two, that's fine. But if there's like a few of them that are really good to know, then it would be good. So like
I may add more stuff into this, and I can update this on GitHub, and I would let you know. But that's something very useful, should be useful. So here what I did is I download the data, then I save it onto my hard drive, and also to be safe, I also save it as a CSV. And as you can see from my R interface, it downloads the data. Each time it downloads 300 at one time. What I want to say is it's slow, because maybe this can avoid being blocked in case they're thinking you're hacking their servers. So, so what I did is I built an if clause that can check if this data already exists. If it already exists, I'm going to just load it. Otherwise, I will download it again. So if you're going to work with 100 species, 1,000 species, this may help you save your time. So next, after we got the data, actually you can see it. You can tap view, V-I-E-W. The V have to be capitalized. If you run it, I don't have it. Oh, it's occurrence raw. If you run it in RStudio, you're gonna see a new window on the top. You can do something similar like in Excel. You can filter your data. You can rank your data, sort your data. You can do a lot of different things. So in this case, you can stay away from those commercial softwares. So occurrence data, obviously we need to do a lot of cleaning before we actually use it. those are here's some following some common things that I usually do, but this is not the best, may not be the best practice. Okay, shall we get started? I think in the morning I forgot to mention something about what is this folder that you downloaded. So I prepared our R script that can generate this HTML file, which is have all the code, all the annotations, and also this is a paper that Cassandra and another colleague submitted, basically something about how to run Maxent in R specifically. And those files are basically I think what you want to look at is the first appendix 1 case study HTML. If you open it, use say Chrome or Firefox, you're going to see exactly this. So even without me, if you install all the libraries, you can run through this step by step. Should be no problem. And the appendix 2 is a small function that we wrote that can help take parameters to the Maxent Java program, but through an easier user-friendly way. And the appendix 3 is basically a list of parameters that are available for the Java interface, but we implemented all the parameters in R. So basically this is a comprehensive list of parameters that you can use in R, basically to do anything that you can do in the user interface, do the same thing in R. And I think I asked you to open the scratch.r over here. This is a script that you can play with your code. And if you have never used RStudio, you can notice there are 4 panels. This top left one is where you can run your scripts. And here this part is maybe the command line that if you want to run some code individually. And this part, you can look at files, you can look at plots, packages, you can also read help document. And the thing over here on the top right-hand side, that's the environment, what is being loaded into the RAM that you can, so you can look at them one by one if you want to make sure you have it. I think the difference between running code in the script part versus this part is if you run anything in the script part, you have a log of what you have implemented, so your research is reproducible. So that's important. This is also the biggest advantage. Say you select a few options in the Java user interface, and you forgot about it 1 month later. It's hard to repeat exactly what you have done. But in R, you can exactly repeat what you have done. You can even set up a fixed seed that always give you the same exact random sample. So that's the best part of R. Okay, if we can continue to the tutorial. We were talking about the raster in the morning. So maybe a little bit deeper about the raster. You can actually look at, so raster is essentially a big table. Each cell has a value, but the difference is that value is associated with a position, say a coordinate system. That's basically a raster. And you can look at a single value of the value of a single pixel in R. For example, we're looking at the bio 1. We can look at all the values of this layer. You can have values. And then bio 1, it will give you all the values. So obviously, we're starting from the corner, so there's a lot of much value over there. And if you look at the length of this, of the values, it should be the number that is the number of rows multiplied by the number of columns. So basically, number of cells. And I can even do something like this. We were talking about the reclassification through a function. But what that function does is For example, I want to make values above 100. I want to make them as 1. Here's what I will do to achieve that. So the values above 1, if they're above 100, so this is going to return you a true or false. I'm going to select those. I can select all those pixels. So in this way, I'm going to only see pixels that have value higher than 100, or if it's none, I can assign a new value to those cells by running this. Or maybe we can, I think in this way, the bio 1 will have a different. Okay, how about I do anything that has temperature higher than 0, makes it negative 100. Looks the map has changed a lot. So all the areas have temperature higher than 0. They're all negative 100. So these are just very basic manipulation of your data in R. And similarly, you can, I think we all know about the bioclimatic variables. Those are all generated from the monthly temperature, monthly precipitation. Similarly, you can get your own bioclimatic variables. Say you want to know the mean temperature of the hottest month, which is not available for in that bioclimatic data sets. So what you are going to do is you're going to look through the pixel value of the 12 months and pick the highest value of the mean value instead of doing that across the whole map. But that's another thing that you can do. I will not demonstrate that here. Okay, to continue on the occurrence data, we're talking about using the GB function to download data, and then the next step is obviously to clean up the data. And since we're doing the niche modeling, we always want a coordinate. So here, this first step is I use the subset of the occurrences based on I don't want the column let and long to be none. So I included records without a valid coordinate. That is what I did. And then if you look at, then I assign the occurrence clean as a new data set. And this can tell you that I included 2,300 records that have no valid coordinates. And also, usually we want to include those duplicated records. So maybe before I talk about this, maybe we should look at the occurrences raw. We can look at the first row of the data set we downloaded by doing this. So there are a bunch of columns. Usually also what I do is I look at the names. So there are a bunch of, I think one of them is latitude, longitude. Those are the columns we can use to filter our data. So go back to the duplicates. Here I checked the duplicates based on latitude and longitude. If any column have the same lat and long, I would only keep one. That's the goal. However, if you have multiple species or have the same or in the same data set, you may also want to consider to add species name. If also you want to say sometimes the same location are collected every year. In that case, you may want to have year as a standard to include duplicates. And the first line of code that I highlighted here is going to give you the true and false. and the length of this dupes variable would be the same length of the number of rows for our data set. So here you can see that I do another selection. So basically, I included all those duplicate records, and there are 1,200 records are included. Another thing I frequently look at is the basis of records. So as Mona mentioned yesterday, so all those different columns, they're defined by the Darwin core. So each column, each field have a definition of what that means. And here, this field is called basis of records. Basically, it describes what is that observation. And there are usually a bunch of tabs, say fossil specimen, human observation, literature, machine observation, and a lot of times unknown. And in the Darwin core, they have a specific definition of each tab. So you may want to, I think it is hosted on the TDWG website, and you can Google it and read it if you don't understand what that is. Sometimes what I do is I try to keep the specimen because that means you have a reliable source that you can resort to. So you can go to the museum, you can check if it is a species or not. So that's kind of more reliable. If it's a human observation, it's kind of hard to validate. So if someone observed something and you don't know if that's true or false, so there's no way to double check it. And also, usually you can see that there are fossil specimens. Since, as Tom and Mona mentioned yesterday, there are the temporal component in the niche modeling. So if they're fossils thousands of years old, obviously the climate has changed for that same location, so you want to include that kind of record. And so here what I did, I only kept preserved specimens. And if you compare the two frequency table, you can see that here I only kept the 900 specimens. So time is also important. There's usually a time attribute within the data that you downloaded. Here is basically a frequency calculation of records collected per year. And the oldest one is the 1855. That may be the first specimen of armadillo that has been collected, and then people give that a name. But we may not want to use this record. So here what I did is, this is a histogram of the data per year. So I try to keep records that are later than 1950. This is not our golden standard. I think ideally the ideal condition is you want to keep your environmental data and occurrence data under the same temporal extent. And some people may argue that climate is quite stable within 10 or 20 years. Some people make this standard more relaxed, say after 1930, after 1940. And so that's, if you can make a good justification for that, that's maybe acceptable. So, but that's not obviously the perfect scenario. So we have to do some cleaning. The next step is to make this data spatial. What we have now is a big table with all those different attributes, text. And now next we want to do is make the spatial. The function is called coordinates. And the last two parameters are the lat and long. Those are the names in that data frame, in that table that we downloaded. And please make sure you put the x-axis first, y-axis after that. So this is important. This is a fixed way to provide parameter to make it spatial. So after we make the spatial, you can plot it. So those are the points. And as we all know that those coordinates should have a spatial coordinate system. So there are a few different ways to do this. If if you know exact what is the coordinate system, you can directly assign it. But in another scenario, if the spatial points already have a coordinate system, and you want to make it transform that into another coordinate system, then you want to make a projection. So here, this is the easier way to define a coordinates. Obviously, nobody can memorize all the different parameters for a single coordinate system. And luckily, there's an online system. It is over here. It's a spatial reference system. So people have defined a lot of those commonly used coordinate systems, and it's all shared online. And by doing this, you can run CRS and then put those parameters there. I think basically the most important thing is the ID. Then you can extract all those already defined parameters into R and use it in R. Here you can see that I'm trying to use a WGS84. This is a coordinate system object. If you run it, you can see it. Yeah, there are a bunch of parameters show up here. This is a lat and long WGS84. Since it's not projected, so there are a lot of parameters that are not specified. And also there are easy ways to get the net 83, which is commonly used in US. But I have an example there, but I'm not going to run it. So I first define this coordinate system object. Now I'm going to assign this system to my occurrence data. So the first part, the CRS, occurrence Unicode, that will return the current coordinate system. But I believe it is, if you do not assign it, it should be empty, unless I have run this before. Looks like so. But after you assign it, I mean, also without assigning the coordinate system, you can plot it. But with it, you can plot it together with other spatial layers, like raster layers or other polygon files. So here we plot this occurrence data with the climatic layer to just get an overview. And you may notice that there are points almost in maybe Canada. So that seems to be an arrow. So we obviously want to exclude that points. So here what I did is I did another filter based on their longitude. So I know what is the longitude, so I can easily remove it. So if any points that are above, I forgot what is west and what is east, but this is between this range, I only kept points within this range and excluded the ones that are not. So that's a lot of filters. So after we got this filtered occurrence data, we want to look at what is the environmental condition at that location. And I think the key function is extract. And the first parameter is the raster layer. The second parameter is the occurrence data. You can understand that as extract climatic condition from this layer by this occurrence data sets. And this is going to return you a table. And for each point, there are going to be one row of environmental conditions. And you can see that those are the conditions for the top 6 records. And I think in the morning when Mona was running Maxent, there are some points that do not have a condition. Say points fall in the ocean, points that are close to the coastline, but when there's no fine resolution pixel to capture that. So we also want to exclude that ahead of time. Want to have that under control instead of relying on Maxent or ignore it. We should ignore that by ourselves. So here what I did is if if the environmental conditions is none, basically means in this table there are going to be no value. Those are the bad records. And you can see the bad records, they have no data. So that if we know the position, then we can ignore them in this part. So usually after I did a lot of filters, what I would prefer to do, I would save my cleaned occurrence data. Otherwise, I have to redo everything every time I run this thing. So everybody, if anyone knows GIS, we know that the shapefile is a commonly used file format, even though it is a very company-defined format. It's commercial. But if it's commonly used, we can save it as a shapefile. The function is easy. It's just called shapefile. With the same function, you can either export file or import file. It's the same function, but you have to write it differently. If it is export file, you only if it is loading the file, you only provide the path of the shapefile. Here I loaded the country shapefile, and I think later on I have a place that can export the occurrence data. So if you want to export the shapefile, the first parameter is the spatial points object in the RAM. The second parameter is the path that where you want to save it. And the last parameter sometimes I use is the overwrite. It's basically you want to overwrite the file or not. If you do not specify that, it is, I think the default is false. It will not overwrite it unless you specify that. I think when I was here, I was trying to load I want to show another example to filter data. Sometimes we want to select points by area, or say by polygon, or maybe by country if you want to restrict your area into one country or maybe a park. Here, this example is I'm trying to limit my points into USA. So what I did, I first loaded a shapefile of countries. Here I only have one parameter, which is the path of the file. And then I look at the attributes of this shapefile. You can do the same thing by looking at the attribute table in ArcGIS. But here, that's the way you do in R. Here I only select one polygon when the polygon's country name equals United States. So as a shapefile, I think it's the shapefile is basically a attribute table plus the parameters of the position of the polygons. So similarly, given that you can manipulate or subselect the polygons by just looking at the attributes. So I select this US, I make it a separate object, then I look at the coordinate system of this shapefile, because in ArcGIS, it may automatically help you transform between coordinate systems without letting you know. And except sometimes it throws some error to you, then you can realize that. But in R, you have to make sure everything are all at the same coordinate system. It may be sometimes you have to write a bunch of new lines, but this is just to make sure you know what exactly you're doing. So and always in ArcGIS, you do some analysis, you never see the source code. There are always underlying assumptions. There are always default parameters. You never know, and you don't want to know until you get some error. But as a scientist, we may want to do those things precisely in R. Okay, I think I have a code here. So before I try to overlap the occurrence data and the shapefile, I want to make sure the coordinate system are the same. If I do not do that, the R is going to give me errors. So what I did is I projected the shape file to the coordinate system of the occurrence data. And the function I used is spatial transform. The first parameter is the shapefile. The second parameter is my target coordinate system. And the new projected shapefile is called US shape PRJ. So in order to know the spatial locations of the overlap status between the shapefile and the occurrence data, I use the function over. And the two parameters are obviously the two spatial objects. However, I want to caution that the position of the parameter matters. So if you run this function, the result is going to be a table. The number of rows will equal the number of rows of your first parameter. So basically, this will tell me, say I have 10 occurrences. The result will be maybe if it is yes, the first point is within the USA. Then the second point is within USA. The third point is not within USA. But if you do this oppositely, if you put the polygon of the US as the first parameter, maybe you're going to only get one result. Basically, yes, this polygon has occurrences in it or not. So the position of the parameter is important. And then I did another filter based on the overlap results. So subset based on the overlap results within USA or outside USA. And you can see the difference. So kind of separated the occurrence data. So that's something else you may want to try when you are working with your own data set. Yeah, so all the steps I mentioned may not be necessary for everyone, but those are the commonly used tools or methods that you may want to use. So the next is a spatial filter. I think Mona and Tom both mentioned this, when sometimes, obviously, you have a lot of points in USA, but less points in South America. And if you just run Maxent, and because, as Mona mentioned in the morning, Maxent tries to limit the predictions to the empirical mean, which is the mean environmental condition of your occurrence data. So the density matters. If there are a lot of points in USA, Maxent would consider USA is more suitable than the rest of the area. And maybe that's not true, because that high density USA is basically a representation of sampling efforts. And commonly, more and more commonly, people use a spatial filter. They try to exclude or try to decrease the sampling bells. This is not the best solution, but it may help. And I have to warn that when you do this spatial filter, say you define the size of a big window, you have lots of points, then you may only keep 1 point per window. The size of the window could be subjective, and I don't know I don't know what's the best solution. Maybe up to a point you think it is not being biased, but that's another. I'm not trying to give you the best practice, but this is something what you can do in R. So here what I did is I called it the function style from XY. The first parameter is the layer, and the second parameter is the occurrence data. The raster layer can be your training data, can be the climatic layer you want to work with. It can also be your very coarse raster layer that you want to work with, 1 degree, 10 degree. It can be anything that you want. That will define the size of this big window. And this function is going to return you the cell number, or in other words, the position of this pixel within that layer. And what we want is we want to only keep one record per window, and then we're going to include all the duplicated positions. If one position shows up multiple times, that means there are multiple points fall in this big window, and we're going to include that. Okay, and then we try to make the points spatially unical. Then we plot them on our map, and we save it. And when I save it as a shape file, I got a warning message. And I'm not sure if you know this or not. In ArcGIS, if the column name is too long, and ArcGIS will not like it, it will make it shorter. That is what is the warning message about. But I can do nothing about it. Okay, up to now, we got our occurrence data cleaned. We make it spatial. We also extract the climatic conditions of our occurrence data. And the next step is to look at our background points. You don't have to worry about this if you run Maxent with that user interface. But if you do this in R, I would highly suggest you do this manually, because it's better under control. So here, what I did, this is just one way that how I do it. People may have a different way to define their study area. What I did, I built a buffer around all the points that I have. And the function I use is buffer. And the second parameter is the length of that buffer, the radius of that buffer. And I think there has been an update to this function recently. Originally, the unit is degree, but I think right now the unit is meters. And here, as an example, I did not project my spatial data onto a project system. So here it's still latitude, longitude by degree. It's not projected, just for easy to demonstrate. But if you're going to do this by yourself, look, the radius is distance. It is a projected thing. So you may want to project your map first before you do this buffer. Okay, so I build a buffer and I plot it. And what I actually want is I want to get a bunch of samples within the study area that I just defined. So before I do that, I want to build a bunch of layers that are only cover this study area. And the function I use is crop. Okay, I do it in 2 steps. I crop first and then I mask. And why I do this is it's faster. Crop, say we have our worldwide map. This is the world claim. This is my study area. Crop is going to crop the raster layer to the extent of my study area. And mask is going to draw this fine boundaries of my study area. And why it's separated into 2 steps, it's faster. If you directly run mask toward this big raster, toward this smaller polygon, it takes a longer time. Okay, so after I cropped my study area, and actually you can take a look at this raster. So it's all cropped to the buffer area that I just created. Okay, to save time, I always save the thing that I've precised. Here what I did, I just exported the raster layers onto my hard drive. You can do this one by one, one layer at one time. You can also do this all together for this all 19 layers. But if you do this, you want to make sure you name them correctly. So the first parameter is the raster object in R, as you all know. The second parameter is file names. If you are going to export, say, 10 files, you want to make a list of names. So you want to be careful about this. So what this start is, it's building a string. The beginning part is the path. The second part is the names of each layer, say BIOL1, BIOL2, BIOL until 19. And the last part is the file format. And this, if you run this separately, this is going to give you 19 names. So you want to make sure you name them correctly. And the next part is the format. So you want to know what is the format you want to use. And I have a table for this. Okay, this is the available format you can export. There's the ASC, the ASCII file, which is commonly used. There are also GTIF. You can actually see this information in the help document anytime that you forgot it, which is super useful, and I use it every day. You just type the question mark, write raster, and you can see the help document. If you forgot anything, read it. So yeah, I read the help document every day. So I also suggest if you forgot anything. Okay, now we have got our cropped raster layer. And next step is going to select points. Here my example is showing to draw random samples from this already defined study area. And before I do that, I fixed my random seed. So I use as 1. This means next time if I do this again, I'm going to get the exact same sample. And this is important because it will keep your research reproducible. I don't know if you notice this when you're using the Maxent. So in the Maxent settings, in the basic, there's a random seed. Your basic by default is not selected, but if you select it, it will give you random background samples every time you run it. So anything that is possible here should be available in R. Okay, so after I select the seed, or after I fix the seed, I try to select 10,000 points from this area. And I have another parameter which is also important, which is I want to make it spatial. So after they got the points, they want to make that already spatial with the coordinate system with it. And you can see after I get the samples, I plot them on the buffered area. Since they're already spatial, so it can be directly plotted on the map. I'm not sure if you know this. There's Phillips, the author of Maxent, helped propose a method called it's a way to draw samples according to sampling BIOS. I think it is also possible to do this in R. If you already have a sampling BIOS layer, you can define the weights, or you can define the number of samples you want to draw from each pixel. So you can also do that manually in R. Another thing is because those samples are drawn from the raster layers, they should already have the associated environmental conditions, and we can double check it. Okay, so yeah, they already have the environmental condition with them, so we don't need to do the extract again. Okay, before we throw the data into Maxent, we want to make sure we separate data that some are used for training, some are used for testing. We want to make sure we do this in the beginning, so that the testing and training can be independent. There are different ways to do this. You can do random samples. You can also do some spatial blocks, and I can talk later. So here's the way that I do random samples to make your study reproducible. since this is just a random thing, you want to select your seed. Here I just randomly make a seed 1. You can also use 100, 1,000, 900, any number that you like. So here I draw that I want to take half of the occurrence data as training and the half as testing. The first parameter is the ID of the rows. It is basically from 1 until 100 if I have 100 rows of records. And the second parameter is basically the number of samples I want to draw. If I have 100 records, here I may want to put 50. I want to select 50 rows. And this is just the ID of that row. And I can use that random select ID to select my occurrence data. Here the I select, here's this select. One is training, one is testing. And if you plot them against each other, you can see that they're generally randomly generated. As I said, there are other ways to cut this. I want to show you a figure. This is a method proposed by the implemented in the NIMBioS package. I think this is done by Robert Anderson's lab. They propose a bunch of ways to cut your file differently. The first one is a little bit like a random sampling, and second one is block separation. They cut the occurrence data spatially into even number of subsets. And I think the reason is they are trying to do cross-validations across space because they have cut their data spatially. I believe that's one big purpose for that. And also there's the checkerboard and advanced checkerboard. I think the goal of those two separation methods is to cut up or to decrease spatial autocorrelation. Basically, they're building small blocks. They're only going to pick one set from one color. So you can see that the red points are all selected from the white area, and the blue points are picked from the black area. And for this method, you can only get 2 subsets of samples. And for this one, I think they're just cutting big blocks first, and then within this big window, they cut smaller blocks. And in this way, they get 4 different subsets. And according to the paper, they believe the following 2 methods, the lower 2 methods, can decrease spatial autocorrelation. And if we go back to our tutorial, I used the function from NIMBioS. This is how you call a specific function from a specific package. This is the package name, this is the function name. Sometimes you have to do this because 2 different packages may have different function but have the same name. If you want to call a function specifically, you have to do this. So the input is basically the location of occurrence data, location of background data, and they're going to help you cut the data set into 4 pieces. And after I cut them, I plot them, and you can see, so they're being cut spatially. I mean, ideally, you can do a lot of, you can run your model in different ways to get the best performance in the testing data set. And for example, if you train your model with the top 3 subset, and if that model can do a very good job in terms of accuracy in predicting the point here, that at least you can say your model is spatially transferable to the South America. Yes?
So these different block designations are defined in the NIMBioS package?
Yeah. Yeah, after you run that,
That's how it designates.
yeah, they're going to give you a row of data, the array will be have 1, 2, 3, 4, represent the 4 groups. You can subselect that based on that value. Yeah, so people doing that, they're trying to get a better spatial transferable model by turning their parameters. And if they can do a good job in transfer predict the spatially independent subset, we may assume they can do a better job in prediction in other areas, though that's our assumption. But at least it's better than without spatial segregation. Okay, but in this example, I'm not using this. I'm just using the random samples. Okay, after we got those occurrence data into training and testing, we also have the background data. We have environmental conditions for both data sets. Next is going to be fit the data into Maxent. We know that if you run Maxent from the user interface, the default way is to provide locations, the coordinates, and a bunch of raster layers. You can do the same thing in R, but since we are already in R, we are already going through all the complex manipulations, then I would suggest you go one step further. You build the data by yourself instead of provide a raster layer, let Maxent do with it. You deal with it. So this is the ideal output for Maxent. You have a column which tells Maxent presence or absence, and 0 here basically means background points. It's not the true absence. And then you have the rest of the column giving you the conditions for this record. And maybe you notice that we do not need location here anymore, because basically the location is giving you the environmental condition. When we got the environmental condition, we don't need the location. This is all Maxent need. So Maxent need 2 parameters. It's P, the presence or absence. X, say the predators or covariance. Okay, so that's ultimately the data format you want to give Maxent. Here's what I did is this is just build this first. Build the first column, 1 or 0, and then the P and A are just the attributes of the environmental conditions for presence and environmental conditions for absence. And now you can throw the data into Maxent. I know that in the morning, a lot of people cannot load our Java, but up to this point, have anyone successfully can do that? Can you successfully load the R Java function in R? Okay. Okay. Up to now, we can run our Maxent models. So it's quite different from running Maxent with that user interface. But the good thing is, before you run Maxent, you can do a lot of manipulations, change all the things that you want or you desired, and given that you have good justifications. Okay, Maxent parameters. As I said, X is the predictor, the environmental condition for presence, environmental condition for background. The P, basically the presence or absence. And the next parameter is the path. This is the path for the output for Maxent. If you do not tell this function what you want to put, this function will automatically generate a folder in maybe your C drive, maybe your D drive, in the temp folder. But I would suggest you specify the path of your output. And the next one is the detailed argument. If you ignore it, Maxent will use the default parameters. But that's not what we want. We want to manipulate the parameters. Okay, if you run this, if you run this, I think two things will happen. They're going to give you an output in the folder that you specified. Output, Maxent outputs. Yeah, this is the folder that gives me the result. You're going to get the exact same output, similar as that you get when you run Maxent in that user interface. You can also look at the HTML file, which is similar to what you get from the user interface. You have everything. But the difference is you get a model that is stored in the RAM in R. It's the model that I just mentioned. It's the model that lives in your RAM, the model that we calibrated. So if you run Maxent in the user interface, you will never see it. You can never touch it. But in R, you can touch it. You can look at all the things that are stored within this model object. And the good thing is you can make predictions, you can make predictions independent from model training. So if you have ever run Maxent user interface, you train the model, you make projections all at the same time, right? You cannot run model, save it, make projection. It's impossible. But in R, you can do this. And in R, you can make since you already have the model, you can predict on a bunch of raster layers. You can predict on a table. You can even just write a bunch of values and let Maxent let the model give you the predictions. So here's an example. The first example is I make a prediction onto a raster layer. You can see the study area is the raster stack, a bunch of layers. Then I make a prediction. The output is also a raster layer. So basically what you provide to the predict function, the same type of data will be returned. You can see that what is being returned is a raster layer, and you can plot it. You can even project towards the whole world, any raster layer that you want to predict. And you can also make prediction, as I said, onto a table that had all the variables that you used to train the model. Here you can see that I'm going to predict the model to P, and here the data that is in P. This is just basically a bunch of environmental conditions. And here the predictions are returned. So this value is returned for the first record. The second value, 0.36, is for the second record. So given that, obviously people may want to fix some data. Say you want to know what is the predicted value for a condition, say BIOL1 equals 1,000, BIOL2 equals 1,000, BIOL3 equals negative 1,000. You can make all those predictions. Here just a histogram of the predictions. Here's another example. I'm only making prediction to the top 2 records, and I got 2 values returned. Okay, so we got the model. We can make predictions. Now we want to think about the model evaluation. And I think model evaluation, you're supposed to evaluate your model using the data set that is independent from model training. In other words, your testing data. And the function I used is evaluate function in the Dismal package. So you have 3 parameters. The top 2 are the environmental conditions for the presence, environmental conditions for the background, and the third parameter is the model. Here I did 2 things. So if you know, so maybe all of you have heard about AOC, you know that there are training AOC, testing AOC, and sometimes they are different, and sometimes they are always different. So what I did is I evaluated the model based on training data, and evaluated the model based on testing data. After you got this evaluation done, you can look at the AUCs. You can look at the number of records being used to evaluate the model. And given this evaluation object, then you can look at the thresholds. So, okay, what this evaluation, what it does is it goes through a gradient of thresholds and then calculates all the matrices in the confusion matrix. And then with that all calculated, you can get the AUC value and maybe TSS, sensitivity, specificity. And then given that, you can think about thresholds. So as Mona mentioned this morning, there are a number of thresholds that you can pick. And there's already a function can help you do this. You don't want to, I mean, if you run Maxent in R, no, if you run Maxent using the interface, you get the, no, not here. You get all the thresholds in your table. If you want to look at all the rest, you want to look at that CSV file that Mona showed this morning. But in R, there's maybe a better way to do it, which is you use the threshold function. Okay, there's a parameter called no omission. And this is going to return you the minimum training presence threshold. Okay, but pay attention that those thresholds are all based on training data. We're not using testing data to calculate those thresholds because we have to decide our threshold based on training data. Then using this threshold, we apply this threshold to the testing data, and then we can get the TSS, sensitivity, specificity. You can also pick the highest TSS. You can also select 10% omission rate. So basically this is, so we know that sensitivity plus omission rate equals 1. And if you put sensitivity as 0.9, the omission rate is 10%. And obviously you can, if you want a 5% omission rate, you can change this parameter. And after you select this, okay, so far so good. Any questions about the thresholds? No?
Do you mean like 5% omission rate sensitivity 0.95 for the one highlighted?
Oh, okay, yeah, that's wrong. That's an arrow, sorry. Okay, after you got the threshold, usually what we want to do is want to transform the continuous value into a binary map. There's the easier way to do this. This is a layer that we already have, and we can plot it. This is our raw prediction, the prediction into our training area. You can use this if the prediction is higher than the threshold, give it a 1, otherwise 0. And we can compare the difference. Yeah, we can show them together. On the left side, that's the raw prediction. This is the thresholded prediction. And another thing I want to mention is sometimes the raw output from Maxent is not preferred because there's no biological meaning, and also that they're not linearly spread out. An alternative way is to use omission rate. Sometimes what I do is I build a bunch of thresholds based on omission rate. say 0% omission rate, 5%, 10%, 50%, then I'm gonna reclassify my layer based on all those thresholds. Say 0 can be below the minimum training presence, maybe about 1 is the above 50% omission rate. So that's kind of in that way, it's kind of a relative value of the predicted suitability.
I have a question kind of general. So about this thresholding thing, wouldn't it be more fair to just to present the logistic output and let the reader decide what threshold or present both? So why you need a threshold? I can see how creating a binary map is maybe more appealing or interpretable, but why obscuring the actual raw output with a threshold when you can maybe present and the reader can assess? Maybe I don't know.
Okay, so the map over here, the left one, this is not the raw output. This is already transformed. So Maxent used a logistic transformation.
Yeah.
But there is not much thing you can say about that. You can say this area is relatively higher than the lower area, than the lower predicted area. And also, if it is your paper, you should interpret it. That's your story. You should not leave the message to the reader. And also, because if I run two models in different extent, say one I use this smaller training area, another one I use the whole world as training area, the scale of the values may be different. So it's not comparable between models.
I would say that if someone sees a map that shows probability of, and a lot of them know that the probability of happening, might say, oh, I should go sample the pixels that are at 0.8 and not the pixels that are at 0.5. Then we know that this is the logical, we know it's that simple, it's not that simple of a translation from the maximum logistic output to
Oh. Okay. 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 So we have run some simple models, mostly use the default setting, but we want to use our personalized models. I think one big thing for Maxent is you want to select the feature that you want. Here, what I first did, I loaded a function. This function would help you formulate the parameters that are going to be given to Maxent, the Java application. And if you want to use default feature, you can do this. So you call this function, basically prepare parameters. What you want is you don't want anything that will use the default. But if you put different feature that you want, Maxent will run it using that feature that has been specified by you. And you can put L for linear, Q for quadratic, and you can read this for the rest. And the order of the feature doesn't matter. You just put that thing there. The function Maxent will know that. And then you can play with this parameter. And I think Tom has later we'll talk about model comparisons based on all those different manipulations and rank the models. But this is just the basic step of how you can run one model as you desired. And another thing you really want to change is that beta multiplier. Or in other words, it is how close you want to fit your data, as Mo mentioned earlier. And here I did an example. I added another parameter. I make the beta multiplier as 0.1. In the second model, I make this beta multiplier as 10. And I got two models. And to show you how they perform differently, here I artificially build the data. Because this model is trained with 3 variables, so the data I fixed or I simulated also have 3 variables. It's about 1, 4, and 11. What I did is I make 2 variables constant, and I build a gradient of about 1. And I believe it is the same thing that is implemented in Maxent. When you see this, you see all those curves. Those are all, they keep one variable varied across the gradient and keep all the rest constant. It's the same thing, but you can define what you want to predict. This is the data set I simulated. I make predictions using the 2 models with using different multipliers. And here's the comparison of the response curve 4 by 1. And this red line is a more relaxed fit to the model, whereas the beta equals 10, the black line is beta equals 0.1. And you can see that there's a big difference of the response curve, and which corresponds to what Mona said. When the beta is smaller, it's a close fit to the data. When the beta is larger, it's a more relaxed fit to your data. And we know that in the Maxent user interface, you can specify the projection layers. And even though you can make this projection independently, in R, you can also do this similar as in the interface. What you need is another parameter called the projection layer. What you do is here you provide a relative path to the layers you want to project to. And the premise is you already have them saved in your hard drive in that folder. And I think another important thing I want to mention is the clamping. So we all know that. So in Maxent's paper, they mentioned clamping, and the clamping is by default 10 data on. But I want to make sure you know what is clamping. So basically what I did here, I trained two models, one with clamping on, one with the clamping off. And I make two models that project on the same layer, and here I compare the difference. And maybe you can notice there are some slightly difference over here. This is the difference between the two predictions. And I think this one example I performed a while ago to see what is the difference. So this is the response curve of when clamping is on. This is when clamping is not on. And clamping basically that is, this is the range of your training data. If you go, generally speaking, it's the range of training data. If you go over your training data, Maxent will do this. But if you turn this off, Maxent will do this. So how do you think? Do you think clamping is good or bad? Or should you leave it on or should you leave it off? Or maybe it depends. Okay, imagine that, say this is the true response curve. And given that your training data is within this area, and we can imagine that Maxent will start climbing from here. And what does this mean? This means making a high prediction in a wide area, even though the truth is maybe the probability or the relative probability is going to decrease. In other scenarios, if the true response curve is a linear function, it just goes above. And sorry, this is not a good example. And maybe, okay, let's use this example. In this case, Maxent start to be conservative, and instead of going down, but going horizontally. And at some scenario, this may be good because it's relatively conservative instead of do real extrapolations, even though we are having a narrow definition of extrapolation. And the clamping function is a little bit tricky in Maxent, especially if you want to use it in R. If you use the user interface, you can easily turn on and turn off. But if you run Maxent in R, and you want to play with clamping, you should do this at all or at one time. In other words, if you trained a model and you want to make predictions, at this time, clamping parameter doesn't work. This is how Maxent is designed. It's not what I want. However, in R, if you really want to play with clamping, you have to turn this on and off, but at the same time make your projection layers within this module so that you can see the difference. Yes?
Sorry, can you clarify then? So if you have, can you go back to the clamp versus no clamp? Yeah, so if you have no clamp, and let's say that it ends at 200, like not at 300, just so I can visually see it, then if you're out of the range, what will happen when you have no clamp on? Like what is the prediction it will generate, let's say, if you're exposed to that value?
I believe it will just naturally follow the original trend.
Oh, so it'll just keep going down.
Yeah, if it is a linear function, it will just directly go linear. It will just follow the very nest, the parameters very nest here.
So this one would just drop down, essentially, in the one.
Yeah. And also different algorithms have different ways to deal with this. I can briefly show this figure. So this is the response curve that we draw as a comparison of a bunch of different algorithms. And you can see that different algorithms make different responses. So the infra does not do clamping, but it directly goes down to 0. And the GM, I believe in the very end, they are generally following the original trend. And Maxent is doing clamping. We have a comparison, but it's not very obvious here. And I think GLM is just ignored the range of your training data. But we have to say that if you make prediction outside your training data, that is extrapolation. That's not the decision of the algorithm. It is your decision. And you have to know that if you do this extrapolation, accuracy is not guaranteed. And it's not the responsibility of any algorithm. It is the modeler's responsibility. If you make a prediction to that's the glacial maximum or to 100 years later, you have to know that you have extrapolations in your prediction. You have to know that the accuracy is not guaranteed outside your training data. I'm not saying you should not do that, but you have to know the underlying uncertainty. That's important. Okay, here's clamping. And okay, the next one is cross-validation. It's probably easier to understand. You can do this in the user interface. You can also do this in R. You just specify the parameters, the number of replicates, and the way you want to do the cross-validation. There are different ways. If they're available for the user interface, they're available for running this in R. Oh, I think I'm on time. The last one is a small experiment. So we have talking about all those different ways to contrast the model. How you select your occurrence data, how you build your training area, how you select background points, how you select features, how you select the beta multipliers. There are numberless combinations of this. And obviously you can evaluate the model for each combination of the parameters. But I want to say that the model can easily achieve a high AUC without a good justification of how you run it. So in the last part, I just do an example. I built two models. One is using a smaller training area, which in theory could better mimic the M, or the accessible area that is always mentioned in the BAM diagram. And the other one is I use the whole new world, which can be sometimes the default when people ignore the importance of training area. So given those two different training areas, I draw random samples from the two training areas. I use the exact same occurrence data. I use the exact same testing data. The only difference is the background data because of the different size of the training area. So after that, I evaluated the model, used the same exact testing data, but the background data are different. Here's the difference of the predictions. The left one is the smaller training area, and this one is the bigger training area. There are some similarities. Say this area all both predicted at relatively higher value, but the difference is here there's a bunch of kind of higher values compared with the bigger training area. And if you look at the AUC value, the left one has 0.65. The lower one with a huge training area, the AUC is 0.9. So what does this tell you? This tells you that if you use a huge training area, you can easily get a super high AUC. But is that a good model? We don't know. Given that we know that the accessible area is important, whereas the second method has this high AUC value, but it may not make sense biologically speaking. And also maybe more, another perspective to look at this is the statistical optimal, say high AUC, may not be always the biological optimal, say the best theory. So that's a conflict. And also another thing I want to say is, given that you can easily get a high AUC value, and maybe you want to think, next time when you look at the model with a high 0.999 AUC, you may want to think about, is that actually a good model? or not. Maybe you should look at how they contrasted the model. Yes.
Yeah. So in this case, the big training data is the one with the higher the better model performance.
Yeah, for this one, the AUC is 0.9.
This is still the armadillo data, right?
What?
This is still the armadillo data.
Yeah, it's the same training data set.
So the big train area actually coincides pretty well with the IUCN area. The one I know the armadillo is there. So
It depends on how you.
training area, I don't like it.
Well, I think this prediction and IUCN map, they're not comparable unless you make a threshold decision first. You can select different threshold. As I mentioned that this area, this prediction in this area is quite similar, like here, right? Potentially, you can select two thresholds, give you the very similar binary map, which both can be similar as IUCN map. So
All the decisions are so important. It's crazy.
yes, Tom.
If you apply the same threshold to small training area and big training area output, to me that would be interesting to look at to see how the map that we want to see on IUCN, how that output is, how different that output is. Because right now we are looking at continuous output, and I can't really tell how much of something could be predicted present versus absent between those two.
I think it's not so much a matter of, oh, the AUC is higher over here and lower over here. It's a matter of being honest with yourself about what is this data analysis telling you. I know you're very focused on there are armadillos in your way, but the point here is we are scientists, we're doing analyses, and we do not want to use a model that is not robust, okay? And by creating some huge training area, we're essentially creating yes-no contrasts that do not exist from the perspective of the species. And so what Xiao is showing us isn't, oh, this one's better on the right and worse on the left. It's the artificial nature of the AUC. AUC is very prevalence dependent. And that is crucial because you will make assumptions about an M which are based on biology and geography. You will submit your data to analysis and you'll see what comes out. And then you'll ask objectively, is this better than that? And the terrible thing is the honest model, the good scientist honest model, may have a lower AUC and may even be not statistically significant, but you're being honest with yourself. So that's the point. This is not a realistic example where we should be asking which is closer to right. This is a model that's just an example.
No, I understand the training nature, but also for this species, for me, it will make sense to use a bigger calibration area because this animal is everywhere.
Right, it's a bigger calibration area. I think if I'm thinking about M, we have to reduce M to what has been sampled. And if you look at the sampling, it's quite limited going north and south and such. So all I'm saying is sometimes doing the right thing in this field means lower statistical power, lower metrics of evaluation, and sometimes not even achieving statistical significance. But being honest and doing the right steps.
A little bit more detailed response to your comments. You're thinking this one is better mimic the IUCN range map. Okay, if you pick a threshold, you can notice that this area may be cropped out. Whereas the IUCN range may tell you this whole area may be suitable. And if you look at this one, this area are generally all suitable. So if you pick a threshold that can capture this, in some way, this may better mimic the IUC range map. So given that I just mentioned the extrapolation, right? This area are probably all extrapolation under clamping. And that's the reason that we should include prediction over here. In that case, maybe make this map better mimic the IUC range map. Yeah, so I think that's the end of this R tutorial. And the last thing I want to say is this tutorial will be always on GitHub. I may put some updates if I find bugs, and I think you can always resort to this. I think everything I explained is going to be a subset of this document.